So we're going to go through the first chapter on secondary one math. That would be actually the prime numbers, HCF, the highest common factor, and LCM, the lowest common multiple. So without further ado, let's do question number 1 over here. List all the prime numbers from 1 to 30. So please remember that prime numbers start from 2. 1 is not a prime number. So we have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. So these are all the prime numbers from 1 to 30. So let's do question number 2. Find the prime factorization of 300, expressing your answers in index notation. So we're going to do the ladder method, meaning you're going to put the 300 over here, right? And then after that, we ask ourselves, can it divide by 2? Yes. So 300 divided by 2 is 150. Can 150 be divided by 2? Yes. So 150 divided by 2 is 75. Can 75 be divided by 3? Yes. Why we start from 3, right, is because 75 cannot be divided by 2. You won't get a nice number if you divide 75 by 2. So we move on to 3. And when 75 is divided by 3, we do get a nice number that is 25. Now, can 75 be divided nicely by 2 or by 3 or by 4? No. Okay, so we don't say by 4, I'm sorry. Okay, the numbers here, right, when we use it, we always, I'm sorry, let me rectify myself. The numbers, when we put it here, we always use the prime numbers. Okay, I mean, it doesn't really mean that you should, but that is my best advice to you. You should always use the prime numbers, So can it be divided by 2? Can 25 be divided nicely by 2? No. Can 25 be divided nicely by 3? No. Can 25 be divided by 5 nicely? Yes. So you put a 5 here. So 25 divided by 5 is 5. And then 5, can it be divided by 2 or 3 nicely? No. But 5 can be divided by 5 nicely. So you do all the way until you reach 1. You stop. And then you look at these numbers here vertically. Well, that would mean that 300 equals to 2 times 2 times 3 times 5 times 5, which is equals to 2 to the power 2 times 3 times 5 to the power 2. Okay, just to let you know, when the question asks you to express your answers in index notation, you can't leave it as 2 times 2 times 3 times 5 times 5. Okay, you cannot leave it like that. You have to leave it in index notation. Index notation meaning write it as 2 times 2 has 2 to the power 2. Okay, 3, well, it's just itself alone. We just leave it as such. And 5 times 5, leave it as 5 to the power 2. Index notation means I want to see the power here. Understand? So that would be for question number 2 over here. Now let's move to question number 3. Using the ladder method, so this is the ladder method we're talking about. Find the HCF, the highest common factor of 45 and 240. So for 45 and 240, right? So here we got two numbers side by side now. So how should you approach this is that you need to find a number that is able to divide 45 and 240 also nicely. So if you take 2 for example, right? 2 can divide 240 nicely, you will get 120. But 2 when you divide 45, you will get 22.5. You can check it in your calculator. So the number isn't very nice. So we don't put 2 here. Then again, remember the numbers you put here, right? Just like earlier, must always be the prime numbers. So we move on from 2, so we move to 3. So we're going to put 3 here. So we put 3 here and we see that, hey, 45 can be divided nicely by 3 to get 15. And 240 can be divided nicely by 3 to get 80. And then now we keep going. Then we check again, 2357, 2357, like so on and so forth. So can 15 be divided by 2 nicely? No, you will get 0.5. So let's move on to 3. Can 15 be divided by 3 nicely? Yes, you will get 5. But 80 cannot be divided by 3 nicely. You will get not a nice number. So then we move on to 5. Can 15 be divided by 5 nicely? Yes, you will get 3 over here. And can 80 be divided by 5 nicely? Yes, you will get 16. Okay, now over here, you will realize that, right, you cannot fill in any number inside anymore because you cannot find a common prime numbers over here. Okay, remember the numbers here must all be prime numbers. You cannot find a common prime numbers such that it can divide both 3 and 16 nicely. Okay, you can try it out. Okay, 3 cannot be divided by 2 nicely. 16 cannot be divided by 3 nicely. 16 cannot be divided by 5 nicely. 16 cannot be divided by 7 nicely. 16 cannot be divided by 11 nicely. Can you see? I'm listing all the prime numbers here. 16 cannot be divided by 13 nicely. So we don't have any other choice anymore. So we stop here. Once you cannot find a factor that can divide these two numbers nicely, you stop. And then what you do is the HCF of 45 and 240, right, would be these numbers here that you have listed vertically. Okay, for HCF, you multiply all of them. So the highest common factor for 45 and 240 will be 3 times 5 equals to 15. Okay, so that is the answer for question number 3. But just to elaborate a bit of this to understand, okay, we are looking at factors of 45 and 240, but more specifically, we are looking for the highest common factor. And it happens to be that we have solved for the highest common factor of 45 and 240, which is 15. So you can check that 15 can divide 50 can divide 45 nicely, and at the same time 15 can also divide 240 nicely. And any number above that, you won't find any other number that can divide 45 and 240 nicely anymore, because 15 is the highest common factor. Can? So that is the ladder method to find the highest common factor. Now, I also want to go through the non-ladder method, which is question 4. If you notice, question 4 and question 3, they are the same. We have to find the HCF of 45 and 240 for both question 3 and question 4. The answers for question 4 will be the same as question 3. It's just that for the difference is that question 3 is using the ladder method, question 4 is the prime factorization method. And I would say that the ladder method is more intuitive. It's easier to follow. The student can understand this very well because they have been through the primary school syllabus, because you are still used to numbers. But question 4 is more at the secondary math level. But question 4, the prime factorization, this method is very powerful. And if you were to ask me as a tutor and a teacher, I would prefer question 4, the method, prime factorization method. I would prefer this method and suggest you all use this prime factorization method more than the ladder method, okay, which I'm going to be going through now. So question 4, okay, using the prime factorization method, find the HCF of 45 and 240. So for this method, right, you have to recall question number 2, how you prime factorize 300. Okay, so we have to prime factorize 45 and 240 separately. So for 45 over here, right, we're going to prime factorize it. So we ask ourselves, start with 2, okay, the prime numbers. Can 45 be divided nicely by 2? No. Can 45 be divided nicely by 3? Yes. So 45 divided by 3 is 15. Can 15 be divided nicely by 2? No. Can 15 be divided nicely by 3? Yes. So 15 divided by 3, 5. Now, can 5 be divided nicely by 2? No. Can 5 be divided nicely by 3? No. Can 5 be divided nicely by 5? Yes. So 5 divided by 5 is 1. So once you reach 1, right, you stop and then you look at the numbers here vertically. So you say that, hey, 45 equals to 3 times 3 times 5. So that is 3 to the power of 2 times 5. Got it? Okay, now we are going to do the 240. So for the 240, right? So we have 240 here. Okay. So 240. Can 240, we start with 2, the prime number. Okay, always start the numbers that you select vertically there will be the prime numbers here. So 240, can it be divided nicely by 2? Yes. So 240 divided by 2 is 120. Can 120 be divided nicely by 2? Yes. So 120 divided by 2 is 60. Can 60 be divided nicely by 2? Yes. So 60 divided by 2 is 30. Can 30 be divided nicely by 2? Yes. So 30 divided by 2 is 15. Now, can 15 be divided nicely by 2? No. Now, can 15 be divided nicely by 3? Yes. So 15 divided by 3 is 5. And then can 5 be divided nicely by either 2 or 3? No. Can 5 be divided nicely by 5? Yes. So 5 divided by 5 is 1. So now once you reach 1, right, you multiply these numbers here vertically. So we have 240 equals to 2 times 2 times 2 times 2 times 3 times 5. So this 2 multiplied by itself 4 times, right? So it's 2 to the power of 4, right? Times 3 times 5. Okay, let me write it below. So when you do the prime factorization method, right? Okay, when you do the prime factorization method, right? What I really want you to do is to, okay, let me rewrite this. Not rewrite, I'm going to arrange it properly. What you have to do actually, right, is, give me a second. You have to arrange the numbers. Here, you must make sure that, the base here 3, you need to align them vertically. The base here 5, you need to align them vertically. So if there's no base 2 here, you must leave a space. Okay, it's like an alignment, vertical alignment. So this is the prime factorization method. Okay, I'm going to write in English for you to find the HCF using the prime factorization method, right? So once you have prime factorized the number 45 and 240 separately using the ladder method, and then you write down the numbers that you have written vertically over here. Okay, you multiply all together, you write here as index form, you write here and then write as index form. Then next, okay, pay attention to this. To find the HCF, right? To find the HCF of 45 and 240, this is the English way of remembering. So I'm going to write in purple. So for HCF, common base, take lowest. So what do I mean by this? Okay, listen here. Do you think that there's base 2 here? No. So there aren't any common base 2. So we ignore base 2. Is there a common base 3 here? Yes, we have a base 3 here for the 45. We have a base 3 here for the 240. So out of these two, we take the lowest, that will be 3. So HCF equals to 3. We are not done. Now, for base 5, 45 have or not? Have. For base 5, 240 have or not? Have. So we take the lowest of these two. So it's just 5. So HCF is 3 times 5 equals to 15. All right, so that would be the prime factorization method lah for question number 4 over here, Ken. All right, let's move on to question number 5. So for question number 5 over here, okay, so earlier, right, we have found the HCF of just two numbers. Now for question number 5, we are going to find the HCF of three numbers now. And here we're going to go back to the ladder method again. Then after that, right, for question number 6, for the same of these three, for the same three numbers over here, 36, 48, and 120, we are going to use the prime factorization method. Okay, so for question number 5, let's use the ladder method. Using the ladder method, find the HCF of 36, 48, and 120. Okay, so here then we have to start from the number 2. Can 36 be divided by 2 nicely? Yes. We get 18. Can 48 be divided by 2 nicely? Yes. We get 24. Can 120 be divided by 2 nicely? Yes. We get 60. Okay, now we keep going. Can 18 be divided by 2 nicely? Yes. Can 24 be divided by 2 nicely? Yes. Okay, so we have 9, 12 here. Can 60 be divided by 2 nicely? Yes. So we get 30 here. Okay, now 9, 12, 30. Can 9 be divided by 2 nicely? No. So 2 is out. Can 9 be divided by 3 nicely? Yes. So put 3 here. 9 divided by 3 is 3. Can 12 be divided by 3 nicely? Yes. So it's 4. Can 30 be divided by 3 nicely? Yes. So it's 10. And then for HCF, right, we stop here. Okay. HCF, we need to make sure. Okay, for HCF, you need to make sure that if you want to put a number here, okay, if you want to put a number here, you must make sure that this number here, the prime number, must be able to divide the three numbers here nicely. But if you were to try, right, you will realize that, hey, I don't think I can find any other prime numbers that can divide 3, 4, and 10 all together nicely. So we stop here, understand? And then once you think that, hey, you are ready to stop, then you multiply all the numbers you have written here vertically, which means that your HCF equals to 2 times 2 times 3. So you multiply all the numbers you have written vertically. So the answer for question number 5 is just 12. Can? Right, let's move on to question number 6. So for question number 6, we have, it's the same question as question number 5. Right, we are supposed to find the HCF of 36, 48, and 120. It's just that here, instead of using the ladder method, for question number 6, we are going to use the prime factorization method. So just like before, okay, we're going to prime factorize every number separately. Okay, some of you may be thinking now that actually, teacher, the ladder method seems to be much easier. But trust me, when you go and do the harder questions, the ladder method will not be feasible. I mean, it will not be the more efficient method, okay? On the other hand, the prime factorization method will be the efficient method. Okay, so let's prime factorize 36. Okay, I'll do it quickly because so far you should understand how to do this already, so I don't want to repeat it. So once you reach all the way until 1, you multiply all the numbers vertically over here, can? So 36 equals to 2 times 2 times 3 times 3. So that will be 2 to the power of 2 times 3 to the power of 2. Okay, for 48, okay, we're going to prime factorize this. Now for 120, okay, we again multiply all the numbers vertically over here. Okay, so once you have done that, right, we are going to align all the base all the same. So 2 to the power 2 times 3 to the power 2. Okay, 48 equals to 2 to the power 4 times 3. 120 equals to 2 to the power 3 times 3 times 5. Okay, so for this type of questions over here, remember what I told you? For HCF, right? I'm gonna repeat it for you again. For HCF, okay, common base, take lowest. Okay, so for HCF over here, we make sure to align all the base vertically. So that it's easier to see, you know. And then if there's no base 5, we leave it empty there. Okay, so 36 got base 2, 48 got base 2, 120 got base 2. So 2 is a common base to all the three numbers, of which out of the three, we take the lowest. So we take 2 to the power 2 times, okay, 36 got base 3, 48 got base 3, and 120 got base 3. So what we're going to do here is out of this 3 here, we're going to take the lowest. So that is just 3. But for 36 and 48, no base 5. Only 120 got base 5. So it's not a common base to all the three numbers. So we don't take anything from base 5. So the HCF is just 2 to the power 2 times 3, which is equals to 12. And as you can see, the answer is the same as the ladder method in question 5 earlier. Can? So that is for question number 6 over here. Moving on to question number 7 over here. So for question number 7, using the ladder method, find the LCM. So LCM stands for lowest common multiple of 12 and 30. So to find the LCM of 12 and 30, right, we're going to use the ladder method. So we're going to put the 12 and the 30 side by side. Okay, do the ladder method. It's the same thing as just now. 12, can it be divided by 2 nicely? Yes. At the same time, 30 can also be divided by 2 nicely. So we get 15 here. Now, 6, can it be divided by 2 nicely? Yes, but 15 cannot be divided by 2 nicely. So we don't put 2. Now let's move on to 3. Can 6 be divided by 3 nicely? Yes. And at the same time, 15 can also be divided by 3 nicely. That will give me 5. And what we're going to do here is we're going to ask ourselves, can we find any numbers that can divide both 2 and 5 nicely? Cannot, right? No more already. We can't find. Okay, we can't find any more prime numbers to divide 2 and 5 nicely. So we stop here and then we multiply the numbers here vertically. Okay, so when we stop already, you know that it's time to stop already. Then you multiply the numbers there vertically. Is it just vertically? No. Okay, for LCM, okay, let me teach you a trick. You must always remember, okay, LCM, the L over here. Okay, the L over here. So then you must, instead of multiplying the numbers here vertically, you must multiply the L. So you must multiply like that. Understand or not? Okay. For HCF earlier, we multiply the numbers only vertically. But for LCM, right, on top of multiplying the numbers here vertically, you must multiply in an L shape. So that is for LCM. You can see that this yellow highlighted part, right? LCM. Multiply the numbers in the L region. So for the LCM, okay, for question number 7, so LCM of 12 and 30 is just 2 times 3 times 2 times 5. Okay, that will give me 60. Okay, so remember you must multiply in the L shape. Okay, with that, let's do question number 8. Okay, question number 8 actually, okay, before I do question number 8, right, sorry. So what does LCM really means? It stands for lowest common multiple. Okay, maybe just to elaborate to you, okay, in purple. So imagine the multiples of 12, you know, right, will be 12, 24, 36, 48, 60, 72, 84, 96, right? 108, 120, agree? And the multiples of 30 will be 30, 60, 90, 120, 150, so on and so forth. And if you take a look, right, for 12 and 30 over here, these are all the multiples of these are their multiples respectively. And you notice that the lowest common multiple, right, is actually 60 over here. Can you see? The lowest common multiple is actually 60 over here. So that is what it is meant by the lowest common multiple. Look at all their respective multiples for 12 and 30. What's the multiple that's common to both of them and also the lowest? So that's the meaning of lowest common multiple. Can? So with that, let's do question number 8. So for question number 8, it's the same answer as question number 7. Okay, we are still being asked to find the LCM of 12 and 30, just that this time we're going to use the prime factorization method. So for the prime factorization method, you do the ladder method separately for 12 and 30. So let's do it here. 12 divided by 2 is 6. 6 divided by 2 is 3. And then 3 divided by 3 is 1. Okay, and then we have 30 divided by 2 is 15. 15 divided by 3 is 5. 5 divided by 5 is 1. Okay, which means that 12 is equals to 2 times 2 times 3. So that is 2 to the power 2 times 3. And then 30 is equals to 2 times 3 times 5. Okay, that is exactly just itself. Can? So far okay with the prime factorization method. Going a bit fast because by now you should get the hang of it. So I don't want to bore the student too much. So I hope that you can understand this now, especially when I'm doing it at a faster pace. That's my style. At the very start, when I intro it to you, I will go through very slowly, methodically, so that you understand what I'm writing for every step. And after I know that I will keep the pace of the lesson. When you're used to it, I will go a little bit faster. Can? So we have 12 equals to 2 to the power 2 times 3. So we align the base now. 30 equals to 2 times 3 times 5. Okay. So now let's bring this down. Okay. So now, unlike HCF, right? For LCM, okay, for LCM, okay, how we do this, the English explanation is all the bases. No need common base, just all the bases. No need to check whether they are common or not. All the bases take the highest. Okay, so if you look at this now, right? Okay, first we make sure that you align the base all vertically. Then for the LCM, okay, LCM will be equals to, okay, we have base 2 here. So we take the highest of the 2. So 2 to the power 2. We have base 3 here, base 3 here. So we take the highest of the 2 times 3. And we have base 5 here, but no base 5 here. But it's okay. All the bases, we take the highest. So we just times 5. So then the LCM in this case is 2 square to the power 2 times 3, okay, times 5. So that will be 60. So that will sum up for question number 8 over here. And you can see over here, right, that the LCM is 60 for question 8 is also the same as the LCM for question 7, which is 60. But I know some of you might be thinking right now that you're not convinced that using the prime factorization method is easier, because apparently the way I see it right now is, yeah, question 7, the ladder method is easier to obtain the LCM. But just let me tell you this, there will be a time where you will realize that the prime factorization will work very well. Is because the numbers I'm using here, right now I'm just introducing you all a new topic. So I'm not using a very big number, but as you deal with a very, very big number, you will realize that the ladder method will not be a very feasible method to use. On the other hand, the prime factorization method will be the best. Okay? So that is for question number 8 over here. For the finding the LCM of just 2 numbers. Later, question number 9 and 10 will be finding LCM of 3 numbers, which I want you to pay very close attention. All right, let's do question number 8 over here. So for question number 8 over here, it is again finding LCM, but back. Question number 9, sorry, I'm so sorry, question number 9. Let's do question number 9 over here. So again, we are still finding LCM we go back to the ladder method again, but the only difference this time is we are going to find the LCM of 3 numbers instead. So we're going to do the ladder method here. We're going to put 16, 20, 30. Okay, I'm going to put a ladder here. Then after that, can 16 be divided by 2 nicely? Yes. So it's 8. Can 20 be divided by 2 nicely? Yes. So it's 10. And can 30 be divided by 2 nicely? Yes. So that's 15. Okay. And then after that, what we're going to do is, can we find any numbers that can divide 8? Okay, sorry, more specifically, right, can we find any prime numbers that can divide 8, 10, and 15 nicely? I don't think so, right? You can't find any prime numbers that can divide all the 3 numbers nicely. But for LCM, right, I want you to pay attention to this question. Okay, so this question 9. But for LCM, right, you don't need to choose a prime number such that it divide all the 3 numbers nicely, especially when it's 3 numbers. So if you're using a ladder method, right, that's the problem. This is the part that will trick a lot of students and cause them to lose marks. Okay, so for LCM for 3 numbers, remember this, if you use the ladder method, yes, you may not be able to find a number that can divide all the 3 numbers nicely, but you can actually put a prime number, okay, a prime number, it's prime number. You can actually put a prime number such that if it can divide 2 out of the 3 numbers nicely, then you can put that number. So what we're going to do here is we ask ourselves, can 2 divide 8 and 10 nicely? Yes. So we take 8 divided by 2. 8 divided by 2 is 4. Okay, and then we take 10 divided by 2 is 5. And then we just ignore the 15. We just put 15 below. It's okay. Because if we can divide 2 out of the 3 numbers nicely, that's fine. And then next we move on. Can 5 divide 5 and 15 nicely? Yes. So if we put 5 here, so we have 5 divided by 5 is 1, 15 divided by 5 is 3. And then the 4, we just put it here, we ignore it, we don't have to do anything. Then now, we look at the number 4, 1, 3 over here, and then we ask ourselves, can we find any number that can divide 2 out of the 3 numbers here? No, we can't do that anymore already. It's like 4 and 1. Can we find any numbers that can divide these 2 nicely? Nothing much. 4 and 3, nothing much. 1 and 3, nothing much. So we can't find any prime numbers that can divide 2 out of the 3 numbers nicely. Okay. So anyway, just for info, we can't find any number that can divide the 3 numbers nicely. Okay, we can't find any prime numbers that can divide the 3 numbers nicely already. We also cannot find any prime numbers that can divide 2 out of the 3 numbers nicely. So then we stop here, and then if you recall, we have to multiply the numbers in an L shape. Okay, not this LCM, so we multiply the numbers in the L shape, LCM. So then you highlight the last row. So therefore, your LCM will be equals to 2 times 2 times 5 times 4 times 1 times 3. Okay, so that will give you 240. So that is for question number 9 over here. LCM is equals to 240. Now for question number 10, okay, please remember for LCM, you have to be very careful, okay? Yeah, so you can put a star on question number 9. Now for question number 10, we are going to do the same question as question number 9. It's going to be the same three numbers. So find the LCM of 16, 20, and 30. But instead of using the ladder method, we are going to use the prime factorization method. So for this question over here, we are going to prime factorize each of the numbers. Okay, 16, 20, and 30. Okay, so we prime factorize them quickly. So which means 16 equals to 2 times 2 times 2 times 2 equals to 2 to the power of 4. Okay, for the prime factorization, we multiply the numbers vertically here. And then we have 20 to be equals to 2 times 2 times 5. So that is 2 to the power of 2 times 5. And then finally, we have 30 to be equals to 2 times 3 times 5. Now we're going to align all their base vertically. Okay, so that will be 16 equals to 2 to the power of 4. 20 equals to 2 to the power of 2 times 5. And 30 equals to 2 times 3 times 5. Okay, we're going to align their bases vertically. Okay, now once you align their bases vertically, right? Remember for LCM, I'm going to write in purple for you. So for LCM, all the bases take the highest. Okay, so for this, the LCM will be equals to, so base 2, all the bases take the highest to the power of 4. Okay, we're going to take to the power of 4 times, well, we only, base 3 just take 3 lor. 3 is the highest, so times 3. And then base 5, we just take 5, that's just the highest. So the LCM over here will be 2 to the power of 4 times 3 times 5. Okay, so that would give us 240. So you can see that using the prime factorization method, we get the LCM to be 240 as well. Same as the answer for question number 9 over here, 240 and 240 here. Okay, so that's for question number 10 over here, Ken, using the prime factorization method to find the LCM. The good news about the prime factorization method is that it is very neat and it can deal with all the questions. And the harder questions would require you to do the prime factorization method. So I strongly suggest that now you're Sec 1, familiarize yourself with prime factorization method. At the back of your head, remember that this is the best method ultimately as you progress to Sec 2, Sec 3, and Sec 4. Let's do question number 11 over here. Question number 11, using prime factorization, find square root of 324. So first, right, we ignore the square root and then we focus on the 324 over here. And then we're going to apply our prime factorization. So if you remember, so we have 324 divided by 2. So that would give us 162. And then we divide by 2 again. That will give us 81. And then we divide it by 3. Well, that will give us 27. And then we divide by 3 again. That will give us 9. We divide by 3 again. That will give us 3, and we divide by 3 again, all the way until 1. And then we multiply all the numbers here vertically, which means that 324 equals to, okay, we can just do a shortcut now, 2 to the power of 2 times 3 to the power of 4. Okay. Again, as I move on to the tutorial on the later part, I expect that you are familiar with what I'm teaching. But I will also guide you on a bit without skipping too much step. Okay. So 324 is 2 to the power of 2 times 3 to the power of 4. So therefore, square root 324, right? You just replace this 324 with 2 to the power of 2 times 3 to the power of 4. So it's square root 2 to the power of 2 times 3 to the power of 4. And then what happens here is that this square root over here, right, will, remember, will divide the powers here by 2. Okay, let me repeat. The square root in blue, okay, will divide the powers in yellow, 2 and 4, divide by 2. So 2 divided by 2 is what? 2 to the power of 1. 4 divided by 2 is what? 2. So 3 to the power of 2. Okay, after you divide it, then you remove the square root over here. So the answer is just 2 to the power of 1 times 3 to the power of 2. That will give you 18. Okay, so please remember how to do this. This is likely to come up for your exam, Ken. So you can actually also verify this in your exam by keying it in square root 324. You will get 18. So that's one way for you to guarantee yourself that 1 mark. Okay, let's do question number 12. It's pretty similar at this point, so I will do it quickly. So we have to use prime factorization for question number 12 to find square root of 900. So the square root of 900, so let's focus on the 900 inside over here. So we have 900 equals to 2 to the power, so we multiply the numbers here vertically, by the way. We have 900 equals to 2 to the power of 2 times 3 to the power of 2 times 5 to the power of 2. And then what happens is square root 900 would be equals to, you replace the 900 here with this. So square root 2 to the power of 2 times 3 to the power of 2 times 5 to the power of 2, right? And then the square root will divide all the powers here by 2. So 2 divided by 2 is 1. So it becomes 2 to the power of 1 times 3 to the power of 1 times 5 to the power of 1. Okay, we divide all the 2's here by 2. So it's power 1 here. And then after we divide, we remove the square root over here, can? So 2 times 3 times 5 will give you 30. And that will be the answer for question number 12 over here. You can actually use your calculator to verify the answer. Indeed, square root 900 is actually equals to 30. Can? So now let's do question number 13 over here. Question number 13. Using prime factorization, find cube root of 216. Okay, again, we focus on the 216 over here. So we're going to prime factorize 216 now. So 216, we're going to put 2. Okay, so we have 108. Put 2, 54. Put 2, 27. Put 3, 9. Put 3, 3. Put 3, 1. So that means that 216 equals to 2 to the power of 3 times 3 to the power of 3. So therefore, the cube root of 216, okay, so I'm going to put 216 here with 2 to the power of 3 times 3 to the power of 3. So the cube root of 216 will be the cube root of 2 to the power of 3 times 3 to the power of 3. Agree? Okay, we put the 216, which is 2 to the power of 3 times 3 to the power of 3 inside. And then what happens here, right, is earlier the square root divide the powers here by 2. Here the cube root will divide the powers, this powers 3 here by 3. So we have 3 divided by 3 is 1, 3 divided by 3 is 1, okay? So it will be 2 to the power of 1 times 3 to the power of 1. Okay, cube root will divide the powers by 3, square root will divide the powers by 2. So we have 2 times 3 equals to 6. And you can verify it in your calculator. Indeed, the cube root of 216 is 6. Understand? So that is for question number 13 over here. Now let's move on to question number 14. Question number 14. We have using prime factorization, find the cube root of 27,000. So let's focus on the 27,000 over here. So 27,000. We're going to prime factorize this. So we're going to divide it by 2. So we have 13,500. And then we divide by 2 again. We have 6,750. And then we divide by 2 again. We have 3,375. Then we divide by 3 again. 1,125. Divide by 3 again. 375. Divide by 3 again. 125. And then we divide by 5 again. 25. Divide by 5 again. 5. Divide by 5 again. All the way until 1. So just like just now. Then we multiply all the numbers vertically. So we have 27,000 equals to 2 cubed to the power of 3 times 3 cubed 3 to the power of 3 times 5 cubed 5 to the power of 3. And then we're going to take the cube root of 27,000. So 27,000, we put it in here. Replace it with 2 cubed times 3 cubed times 5 cubed. Which is 2 to the power of 3 times 3 to the power of 3 times 5 to the power of 3. And then for cube root, right, again, we divide all the powers here by 3. So 3 divided by 3 is 1. So it becomes 2 to the power of 1 times 3 to the power of 1 times 5 to the power of 1. So then the answer here is just 30. Okay? And if you actually verify this in your calculator, you can see that the cube root of 27,000 is indeed 30. Okay? And we are done with question number 14 over here. Now let's do question number 15. So for question number 15, right, list all the perfect squares from 1 to 100. So perfect squares, right, basically, how I'm going to teach you is you number from 1 to 10, okay, in a way lah. And you square all this number. 1 square means 1 times 1 is 1. Okay, 2 square means 2 times 2 is 4. 3 square means 3 times 3 is 9. 4 square means 4 times 4 is 16. So on and so forth. Okay. So these numbers here, they are my perfect square. You understand? So that's how you can do it. So in a way, you can see that list all the perfect square from 1 to 100, right? So these are my answers. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. So these numbers are derived from squaring the numbers from 1 to 10. Can? So that's for question number 15 over here. Right, question number 16. List all the perfect cubes from 1 to 100. So again, you can start by numbering from 1 to 10. But actually, we can just stop at 6 because we want the perfect cubes from 1 to 100. So we cube the numbers over here. So 1 cube means 1 times 1 is 1. 2 cube means 2 times 2 times 2 is 8. 3 cube means 3 times 3 times 3 is 27. 4 cube means 4 times 4 times 4 is 64. 5 cube means 5 times 5 times 5 is 125. And 6 cube means 6 times 6 times 6 is 216. Okay? So if you think about it, these numbers here are all the perfect cube. So from 1 to 100, all the perfect cubes, well, you will just take away the 124 and 216. So that will be my answer for question 16. From 1 to 100, the perfect cubes will be 1, 8, 27, and 64. Okay? And we are done with question number 16 over here. Okay? Right, moving on to question number 17. Okay, question number 17. Express 1386 has a product of its prime factors. So for this question over here, we are going to do the prime factorization. So dividing by 2, we have 693. And then dividing by 3, we have 231. And then we can divide by 3 again. We have 77, and then divide by 7 again, we have 11. And then we divide it further, divide by 11, we have 1. So do it all the way until 1, and then we multiply all the numbers here vertically. So we have 1386 equals to 2 times 3 square times 3 to the power 2 lah, okay, times 7 times 11. Okay, so this question 17 part I, right, the hence part and part 2, II, for this two is something that you have just seen. This is new to you, so do pay attention. I'll go through it slowly. Hence, find the smallest positive integer k such that 1386 k, which means 1386 times k, is a perfect cube. So we know that 1386 is 2 times 3 square times 7 times 11, right? So therefore, 1386k is just 2 times 3 square times 7 times 11 times k. Okay? Do recall just now I tell you this is 1386 times k, which is here, which is 2 times 3 square times 7 times 11 times k. Okay, and then so what you have to do here is, in order for 1386k to be a perfect cube, so you can remark over here, okay, in purple, for 1386k to be a perfect cube, all the powers must be a multiple of 3. Okay, meaning all the powers here must be a multiple of 3. And So now do pay attention to me. Okay, so I'm going to purposely put power 1 here. This is 2 to the power of 1 times 3 to the power of 2 times 7 to the power of 1 times 11 to the power of 1. Okay, so we know that 1386k is 2 to the power of 1 times 3 to the power of 2 times 7 to the power of 1 times 11 to the power of 1 times k. So to make this a perfect cube, you have to make sure that all the powers here are all multiples of 3. And how you do that is you have to choose k in such a way for this to happen. Okay, for what to happen? For all the powers to be a multiple of 3. So here's the part that you must listen. So what, do you think 1 is a multiple of 3 or not? No, right? Okay, so I'm going to put k here, k equals here first. So what is the number after 1 that is a multiple of 3? Okay, maybe let me rephrase again. What is the smallest number after 1 that's a multiple of 3? 3, right? So how do you get from 2 to the power 1 to become 2 to the power 3? Your k must be 2 to the power 2, right? Agree? Because we want to choose k such that it's a perfect cube. So to make it a perfect cube, I need all the powers here to be multiple of 3. So the number after 1, okay, or the smallest number after 1 that is a multiple of 3 is the number 3. So to get 2 to the power 1 to become 2 to the power 3, I need my k to be 2 to the power 2. So you think about it this way. 2 to the power of 1 times what give you 2 to the power of 3? Times 2 squared. Because 2 to the power of 1 is 2, 2 squared is just 2 times 2. So 2 times 2 times 2, you multiply itself 3 times, you get 2 to the power of 3. Understand? So we need k to be 2 squared, one of it. Then next, is the power 2 here multiple of 3? No. What is the smallest number after 2 that's a multiple of 3? 3. So I want 3 to the power of 3. So 3 to the power of 2 to 3 to the power of 3, how do I get it? I need k to have another times 3. So that 3 to the power of 2 times 3 will give me 3 to the power of 3. Understand? Now, is 1 here, okay, I'll do it slowly. Is 1 here a multiple of 3? No. What is the smallest number after 1 that's a multiple of 3? 7. What is the smallest number after 1 that's a multiple of 3? 3. So 7 to the power of 3. So how do I get from 7 to the power 1 to 7 to the power 3? Right? 7 to the power 1 times what? Give you 7 to the power 3 times 7 to the power 2. So I must put 7 to the power 2 over here. Understand? Because 7 to the power 1 is 7. 7 to the power 2 is 7 times 7. So 7 times 7 times 7 multiplied by itself 3 times is 7 to the power 3. Understand? Same thing here. What is the number 1 here a multiple of 3? No. What is the smallest number after 1 that's a multiple of 3? 3. So this must be 11 to the power 3. How do I get from 11 to the power 1 to 11 to the power 3? I need k to have a 11 to the power 2 here. Understand? So that is how you choose the smallest k. Okay, why smallest? Because what we have done here is we have chosen the next smallest multiple of 3. And then that would be enough to make 1386k to be a perfect cube. Okay, so that's why the smallest k will just be k equals to 2 to the power of 2 times 3 times 7 to the power of 2 times 11 to the power of 2. Hopefully you all understand this. Objective is to force all of these powers here, right? For each base, see this power here, must force it to the next smallest multiple of 3, which is 3. And to do that, we need to choose k so that it can multiply accordingly. So k, if you think about it, okay, 2 to the power 1 times 2 to the power 2, I get 2 to the power 3. 3 to the power 2 times 3, I'll get 3 to the power 3. 7 to the power 1 times 7 to the power 2, give me 7 to the power 3. And 11 to the power of 1 times 11 to the power 2, give me 11 to the power 3. So we get what we want. That is all the powers here are 3. So that is a multiple of 3. And then it will be a perfect cube. Okay, objective is to get all the powers here to be multiple of 3. So that is how we do it. And k here, you need to evaluate it out. It will be 71148. Got it? Okay, let's do part 2. Okay, so for part 1 over here, right, it's like we are adding to the power. Can you see or not? This power 1, we add it to get to power 3. This power 2, we top up to get to power 3. Same thing for here. The power 1, we add 2 to get power 3. Power 1, we add 2 to get power 3. But for part 2, right, part 2 will be remove the power. Okay, here we allow it to increase. You see, from 1 to 3, from 2 to 3, from 1 to 3, from 1 to 3. But for part 2, right, it will be you remove the power. Okay, how we know is usually if the question is like 1386 times k, right, then you increase the power, like from 1 to 3, 2 to 3, 1 to 3, 1 to 3. But if it's 1386 over k, like that k is in the denominator, is being divided, then you remove the power. Can? So let's do question 17. Okay, this is part I, by the way. Let's do question 17 part 2. Notice that I go through slowly if it's something new to you, because I don't want to go through very quickly, especially if it's a new question. Then students wouldn't be able to keep pace. Okay, so find the smallest positive integer k such that 1386, okay, 1386 over k is a perfect square. So 1386 over k. So what is my 1386 from earlier? K is 2 to the power of 1 times 3 to the power of 2 times 7 to the power of 1 times 11 to the power of 1. Okay, over k. Okay, usually we don't put the power 1, but for the sake of explanation and your learning, I put the power 1 there because from my understanding from the past few years, writing the power 1 is essential so that some students can see it. If not, they will struggle. So now, what we're going to do here, right, is, okay, make a comment. We want it to be a perfect square. So in order for it to be a perfect square, right, so for 1386 over k to be a perfect square, all the powers must be a multiple of 2. Okay. So now let's take a look over here. So I'm going to write k equal below again. So this power 1, is it a multiple of 2 or not? No, right? But here, remember, we are removing. We cannot go higher than 1. We must go below 1. You agree or not? But the thing is, right, below 1, then what else? There's nothing else, right? So what you do is you just completely remove this 2 to the power of 1 by putting k as 2 to the power of 1. Okay, so if you let your k here, okay, I write in purple. If you let your k here be 2 to the power of 1, right, one of it, right, then you can just cancel this. You understand? So here we are removing. For part I, we are topping up. We are increasing the power. But here we have to reduce the power. So the number below 1, that is a multiple of 2. Okay. So there isn't really any that you can think about, right? Correct? So here we are removing power. So what is the interesting thing is, right, what is the number below 1? Okay, let me elaborate in this way. What is the number below 1 that is a multiple of 2? 0, because 0 is a multiple of every whole number, right? So 0 is a multiple of 2. So here we are removing. So what's the number below 1 that's a multiple of 2? 0. So to get to 2 to the power of 0, right? To get to 2 to the power of 0, right? I have to, you just think of it as eliminating 2 to the power of 1 entirely. So you put 2 to the power of 1 here. Now, here we look at, hey, this is power 2. Is this a multiple of 2? Yes, right? Then we don't touch. We're not going to do anything. Okay? Now, this is 7 to the power of 1. Same thing, power 1 as well. So, like just now, we need to remove, right? What's the number below 1 that's a multiple of 2? 0. So we just completely get rid of it. So we put k here times 7 to the power of 1. And then same thing over here, 11 to the power of 1. The power of 1, what is the number below 1 that's a multiple of 2? 0. So we put times 11 to the power of 1 here as well. So that you see, when your k is 2 to the power of 1 times 7 to the power of 1 times 11 to the power of 1, right? You cancel. What happens is 1386 over this k, right, that you have selected, right? It's just 3 to the power of 2, you know. And yeah, that's good because for this base 3 only, right, the power is 2 and it's a multiple of 2. So it is a perfect square because all the powers here is a multiple of 2. 3 to the power of 2, power 2, multiple of 2. Can? So therefore, your answer for k is just 2 times 7 times 11. So the answer is just 154. So that would be the answer for question number 17 over here. Right, let's move on to question number 18. Okay, question number 18 is more like a word problem, but it's actually very easy. Is you need to decide whether is it HCF or LCM. So when this type of questions comes up for your weighted assessment or exams, right, it's easy, but you have to decide whether to use HCF, highest common factor, or LCM, lowest common multiple. Can? So question number 18, the school bell of Bedok East School goes off every 35 minutes, sorry, while the school bell of Bedok West School goes off every 40 minutes. The first bell of both schools goes off at 0725. What is the next time that the bells of both schools go off at the same time? So for this type of question, right, let me give you a pro tip and a shortcut. Whenever we talk about, three things happening at once or two things happening at once, like for example, like at this time we will meet together or the alarm clocks will ring together at the same time. It's like um, it's like things happening together at one point. It will be an LCM question. You understand? So what we're going to do is we are going, because they say that the school bell goes off every 35 minutes for Bedok East and the school bell goes off every 40 minutes for Bedok West. Then what we're going to do is we're going to write 35 here and we're going to write 40 here. And then we're going to do the ladder method. If you want, we can do the ladder method, okay? So then we're going to put 5 here. So that would be 35 divided by 5, 7, 40 divided by 5, 8. Okay, so now we ask ourselves, hey, can we still divide it further, the 7 and 8? Not really. So the LCM will just be multiplying all the numbers in this L over here. So LCM equals to, by the way, this is the time taken for the school bell to ring in every 35 minutes for Bedok East. And every 40 minutes, the school bell will ring for Bedok West. So we find the LCM first. Then we know when will the two bells of both schools go off at the same time. I'll explain to you why LCM. So for now, we find the LCM first. 5 times 7 times 8. Okay, so this will give you 280 minutes. Okay, so let me explain to you a bit why when we talk about things happening at the same time is LCM. So every 35 minutes, the school bell of Bedok East will ring, and every 40 minutes, the school bell of this Bedok East, and every 40 minutes, the school bell of Bedok West will ring. So let's look at the multiples. So do you notice or not? They will ring together after 4 hours. Oh, sorry, not 4 hours, sorry. They will ring together, I'm sorry. They will ring together after 280 minutes. Do you agree? It's like from the start until here, right? This bell that is ringing at this particular junction would ring after 280 minutes. Same goes for this one. This one will ring after 280 minutes, meaning after 280 minutes, these two bells for Bedok East and Bedok West will ring together at the same time. You understand? So what we have here is, hopefully you understand this. So what we're going to do is we have 280 minutes. We need to convert it to hours. So it will be 4 hours, 40 minutes. Okay, 1 hour is 60 minutes, by the way. So since the first bell of both schools goes off at 0725, okay, 4 hours, 40 minutes later, okay, you will try your own to do this. Hopefully you can. It's 1205. That will be the next time that the bells of both schools go off at the same time. So how I do it is I just break it down, you know. First I say, oh, 7:25, right, AM. After 40 minutes will be 8:05 AM. Agree? And then 4 hours after 8:05 AM will be 12:05 PM. So that is how I do it just now. Can? To break it down into a smaller subset of problem and then finally get the answer. Can? So that's for question number 18 over here. Now let's do question number 19. Okay, for question number 19, 1,155 bottles of hand sanitizers, 462 thermometers, and 924 packets of masks were collected in a fundraising activity for needy families. The items were packed into gift bags for each family. Each gift bag has the same number of bottles of hand sanitizer, thermometers, and packets of masks. Find the greatest number of gift packs packed. Okay, so for this type of question over here, right, whenever you talk about distribution of items, then it's HCF. Okay, so that's the pro tip I can give you. So what we're going to do is we have 1155 462 924. Okay, so far okay. All right. Okay. The reason why this is HCF, right, is because each gift bag has the same number of bottles of hand sanitizers, thermometers, and packets of masks. Okay. So in order for you to have the same number, right, then you need to make sure that you find the HCF lah. So that is how things are. Then you can later find the greatest number of gift bags. So we're going to do the ladder method here. So now we're going to put the 3, okay, 1155 divided by 3 is 385. 462 divided by 3 is 154. And 924 divided by 3 is 308. And then we have 385 divided by 7 is 55. 154 divided by 7 is 22, and 308 divided by 7 is 44. And then we divide it again. 55 divided by 11 is 5, 22 divided by 11 is 2, and 44 divided by 11 is 4. And then we cannot divide it any further, so we multiply the numbers here vertically. Can? So we have HCF equals to 3 times 7 times 11. And that would give us 231. Okay, so yeah, that's it for question number 19 over here. The greatest number of gift bags, the gift bags packed will be 231 over here. Can? So maybe I try to illustrate to you using a simple example. So for example, right, you have 2 chocolates, 4 strawberries, and 6 oranges. I want you to find the greatest number of gift packs packed. Okay, it's the same context. How would you do it? You know, and of course, one more thing is that each gift bag, right, must have the same number of chocolate, strawberry, and oranges. So if you think about it, right, we do the HCF. So put 2 here. So 1, 2, 3. So the greatest number of gift bag will be 2. Agree or not? HCF is just equals to 2. Why? Because if the number of gift bag is 2, right, that means that 1 gift bag over here, okay, 1 gift bag over here will have 1 chocolate, 2 strawberries, 3 oranges. And because there are 2 gift bag, right, the other gift bag, same thing, 1 chocolate, 2 strawberries, and 3 oranges. So it's like every gift bag, they will have the same number of chocolate, strawberries, and oranges. So that is why the greatest number of gift bags, right, you will use HCF. So it's just 2. Because then you will say that, oh, 2 will be the greatest number of gift bags such that each gift bag will have the same number of the 3 items. So let's go back to question 19. By doing the HCF, you will ensure that the greatest number of gift bags packed will be 231, and then such that in each gift bag, right, in each of these 231 gift bag, it will have the same number of bottles of hand sanitizers, thermometers, and packets of masks. Okay? Because of this thing called the highest common factor, you will ensure that this will be the greatest number lah. Can? Yep. So so if you think about it, right, 2 is a factor of 2, 4, and 6. But I could easily also say that 1 is a factor of 2, 4, and 6, right? 1 is obviously a factor of any number. So I could pack as 1 gift bag. But the issue is that if I pack it as 1, then that's not the greatest number of gift bags. Understand? So I'm just going to erase this, and that's it for question number 19 over here. Got it? Moving on to the second last question, question number 20. So for question number 20 is this is the challenging one. Okay, so do pay attention. The lowest common multiple, this is actually just working backwards. So in fact, for most of the questions here in this practice paper, we have been doing the forward direction. Now it's time for us to do the backward direction. So without further ado, let's do question 20 over here. The lowest common multiple of 2 numbers is 6,804. The highest common factor of these 2 numbers is 567. Both the numbers are greater than 567. Find the 2 numbers. So this question over here, here's how I'm going to teach you to do. First, we prime factorize 6804 first. So let's do it slowly. Okay, divide by 2. We have 3402. Divide by 2. We have 1701. And then divide by 3. We have 567. Divide by 3. We have 189. And then divide by 3 again. We have 63. Divide by 3 again. We have 21. And then divide by 3 again, we have 7, divide by 7 again, all the way until 1. Then we multiply all the numbers here vertically. So we have 6804 to be equals to 2 square times 3 to the power of 5 times 7. Okay, and also we also would like to prime factorize 567. So 6804 here is the LCM of the two numbers. 567 here is the HCF of the two numbers. So let's prime factorize 567 here as well. So we have divide by 3. So we have 183. 189, sorry. And divide by 3. 63 divide by 3. 21 divide by 3. 7 divide by 7. 1. So that means that 567 over here, right, is equals to 3 to the power of 4 times 7. Okay, so what we're going to do here is I'm going to rewrite everything properly. So LCM, which is, okay, I'm going to write it like that now. LCM is 2 to the power of 2 times 3 to the power of 5 times 7. Okay, maybe I put it, yeah, times 7. And then we have HCF to be 3 to the power of 4 times 7. Okay, maybe I move the 7 a bit to the right because there could be a base 5, we don't know. Okay, so my LCM of the two numbers and HCF of the two numbers are here. So now let's first number, second number. So we need to work backwards. So now let me recall what we're going to do here. So HCF, right? Remember, common base, take lowest. LCM, all the bases, take highest. So now we are just doing the reverse. All the time we have been given the two numbers, then we find the LCM and HCF. We have been doing the forward direction. So the hard part is give you the LCM and HCF now, find for me the two numbers. So it's like more like a guess and check, but using this purple statement to help you. Okay? So let me recap again. HCF, common base take the lowest, and LCM, all the bases take the highest. So now we have to really do this now. Okay, so we have LCM here. Let's look at base 2. LCM got 2, got base 2. HCF don't have base 2. So, but LCM got 2 to the power of 2, right? HCF don't have anything, which means that one of the number must have 2 to the power of 2. Okay, but the second number here, right, you cannot have anything because your HCF don't have base 2. If your HCF do not have base 2, remember, HCF means only when I have common base, then take the lowest, then you will have. So if HCF don't even have base 2, that means that there are no common base 2 for both this number here. So we don't put. If first number we put 2 square, right? So the LCM here can have 2 square. Then the second number here, we don't put anything anymore. Because then that will ensure that HCF don't have base 2. But we also put one of the number here as 2 square so that the LCM here will have 2 square. Okay, LCM, all the bases take highest. Follow so far? Okay, now we look at base 3. Oh, base 3, you see? Base 3, the LCM is 3 to the power of 5. And then the HCF here is 3 to the power of 4. So LCM means, we do the HCF first. So HCF here we have, HCF here is 3 to the power of 4, right? And I recall, HCF means both common base take the lowest. So I should maybe give the second number lah. We just guess and check. So second number, I give it as 3 to the power of 4. And then the first number, I'll give it 3 to the power of 5. So now we can say, hey, HCF of these two is what? Okay, we have common base, we take the lowest, 3 to the power of 4. And then that's HCF, common base, take the lowest. LCM, all the bases, take the highest. So base 3 here, we take 3 to the power of 5. Okay. And next, we have both the LCM and HCF to be 7. So perhaps I can just multiply by 7 here and multiply by 7 here. Okay. The reason why both, in this case, I'm guessing that both, in this case, both will be 7 is because your HCF got 7 means that both of this number must have base 7. So that HCF common base take the lowest, both got common base, we take the lowest, so 7. And LCM, you cannot put anything more than 7 for these two over here. Because LCM, all the bases take the highest, so you must make sure both are base 7. Okay? So it's like working backwards is hard, admittedly it's hard. Okay, and then what we're going to do here is to evaluate the first and the second number. So the first number here is 6804, and then the second number here is 567. But here's the issue. Okay, both numbers are greater than 567, but 567 here, right, is not greater than 567, you know. Numbers that are greater than 567 will be 568, 569, 570, then 571, so on and so forth, right? So that means that our guess is wrong. So I purposely make it wrong, okay? So then how do we rectify this? Because we must have both numbers to be greater than 567. 6804 fulfills the condition, but not 567. So how do we do this then? Okay, so I'm going to tell you how, right? So let's look at these two numbers over here. Ken? What we are going to do is we are going to swap these two. Okay, these two numbers. We're going to swap these two numbers. So instead of this being 3 to the power of 5, I write it as 3 to the power of 4. Then instead of this as 3 to the power of 4, we write this as 3 to the power of 5. Because now you will realize that, because it's a guessing game, now you realize that it still makes sense. Okay, let's go through the HCF. HCF, okay, both got common base, right? So we take the lowest, 3 to the power of 4. It fulfills. And then the LCM, all the bases take the highest. So just take 3 to the power of 5. It also fulfills. It's correct. So what we have done here is we have compensated by lowering this number and making this number higher. So let's check now. Okay, let's evaluate again. So 2 to the power of 2 times 3 to the power of 4 times 7 is 2268. Is it more than 567? Yes. And then we have 3 to the power of 5 times 7 is 1701. Is it more than is it greater than 567? Yes. So therefore, the two numbers are 2268 and 1701. Okay, so this question is hard, but actually it's easy if I do the forward direction. Basically, I give you 2268 and 1701. Okay, and then I tell you to prime factorize 2268 into this, prime factorize 1701 into this, and then use this two method to find the LCM and HCF. The forward direction will be very easy. It's just that the backward direction is harder. You have to guess your way through. Understand? So that is for question number 20 over here. Okay, the two numbers are 2268 and 1701. Right, let's move on to the last part of this question before we call it a day. So question number 21 over here. Find the smallest positive integer value of k for which 105k is a multiple of 49. Okay, so this is the last part that I want you to know. Again, it's a new one. So for this type of question, right, like they say, oh, find the smallest positive integer value of k. So first, you prime factorize that number beside the k, 105. You know, that number, that numerical number. So we're going to put a 3 here. So this is 35. Put a 5 here. 7. Put a 7 here. That's 1. So therefore, okay, once you reach until 1, you multiply the numbers vertically here. So 105 equals to 3 times 5 times 7. So that means that 105k, right, would be 105 times k, right, which is 3 times 5 times 7 times k. Okay, so this is my 105. And then this is my k. So how do you make this to be a multiple of 49? Okay, so note that 49, right? Okay, so we do the 49 prime factorize is 7. 49 divided by 7 is 7. 7 divided by 7 is all the way until 1. So 49 equals to, multiply the numbers here vertically, 7 to the power of 2. Okay? So in order for 105k to be a multiple of 49, we need to see 7 to the power of 2 in its prime factorization. Okay? Because 49 is 7 to the power of 2. For 105k to be a multiple of 49, you need to see 7 to the power of 2 in this prime factorization. So we have over here, this is 7 to the power of 1, right? So like I said just now, we need to see 7 to the power of 2 in the prime factorization. We have 7 to the power of 1 here. How do we get from 7 to the power of 1 to 7 to the power of 2? Okay, how do we get from 7 to the power of 1 to 7 to the power of 2? Then we need k to be 7, no? So therefore, k equals to 7. So that when your k equals to 7 over here, right? Then 7 to the power of 1 times 7 is 7 to the power of 2. So you see the 7 to the power of 2 in the prime factorization, where 7 to the power of 2 is 49. Then 105k is a multiple of 49. Okay? Because if you take 3 times 5 times 7 to the power of 2, right? Then obviously that number is 3 times 5. Okay? 3 times 5 times 7 to the power of 1. K is 7. So it's 3 times 5 times 7 to the power of 2. You take 3 times 5 times 7 to the power of 2. What is 7 to the power of 2? 7 to the power of 2 is 49, right? You take this number times 49. Then obviously this number is a multiple of 49. Understand the rationale? So hopefully you see it, okay? So in my tutorials, I'm not the teacher to give the quantity type. I'm more like the kind to give you the different variety of questions that you may be tested. So I expose you to a different variety. So that's how my practice worksheets are structured. Okay? So that's for Sec 1 Math, Primes, HCF, and LCM. Moving forward, we'll be doing the mock paper later.